to Cloud on Air. My name is Jay Jenkins. I'm a customer engineer based here in Singapore. In our previous session, Smart Parking was talking a lot about their IoT implementation and how they took advantage of IoT Core and our Google Cloud Platform services. And I noticed in the comments that there was some discussion around actually having a live demo. Well, luckily, we have Marco Lepisto here from our Solution Architecture team, a proud member of the Geek Squad, to do exactly that. So let's take a look at IoT and how that can be implemented on Google Cloud Platform in a live demo. Remember that at any time you can ask a question below, and we have experts standing by ready to assist. Also, if you have any friends who might be interested in this, feel free to forward that link to your friends so they can register and see this live demo as well. So with that, I'll invite Marco to come on, and we'll do a live demo. Great. Thanks, Marco.
Excellent. Thanks, Jay. Hey, everybody. Just let me unlock my laptop and let's get going. So, welcome from me as well. I'm Marco. I'm part of the Geek Squad. Thank you, Jay. So in this session, I'd like to talk to you about Internet of Things, or IoT. So I'm a solution architect in the Google Cloud team. Let's start with a short introduction, and I'll try to keep the slides short and focus on the demo for you guys. So when you are implementing an IoT solution, doesn't matter what kind of IoT solution it is, hopefully you will be successful. What does success mean? Success means that you have a lot of customers, and also with IoT, success may mean that then you have a lot of devices out there in the field. So there are basically three key challenges for IoT solutions of any type. The first one is security. Because when you think of a normal solution which doesn't have IoT, mostly it's software running in some data centers, in some big servers like in Google data centers. Now those data centers are highly secure, but with IoT, there is an additional challenge that the devices are literally out there. The IoT devices might be in the bus stops, or in the fields, or in the sea, or in your home, in your customer's home. So things like physical access security are an additional challenge with IoT. So security is arguably even more important with IoT solutions than normal solutions, non-IoT solutions. Scale is the second one. So like I mentioned, if you get successful, you may have a lot of customers and a lot of devices with IoT. You may have thousands, even millions of IoT devices that you need to manage. You need to know where they are, what is their state. They are all sending data, likely, things like telemetry, sensor readings. And every once in a while, you need to update those devices, and you need to send commands to those fleets of devices. So scale is easily a good problem to have with a successful IoT solution. And then last but not least is insights. It's not enough for these devices to stream data, send telemetry and sensor readings. You need to actually use that data to drive your business, to develop your new features, to focus on your customers, to make things better. So getting insights from this data is really important. So to make this easier, last year, Google launched the Cloud IoT platform. And the point of Google Cloud IoT is exactly to make IoT easier to create as a solution, to be secure, scalable, and give you the data insights. So at the core, literally, of Google's IoT solution is our Cloud IoT Core platform. It's a service that basically lets you connect your physical world devices on your left there with the rest of your systems and software on the right-hand side. So think of Google Cloud IoT Core as a bridge and a gateway to help you connect and manage securely all those devices, or fleets of devices, and then connect them to the rest of your system. And the Google Cloud IoT Core basically has two main functionalities. The first one is a protocol bridge. And the protocols we support are HTTP, and even more importantly for IoT, MQTT. MQTT is a really lightweight transport protocol that is great for IoT devices. It's better for battery life. It's less chatty on the network, so it transmits less. It's compressed. It's overall better for really small constrained devices with very small and maybe high latency, high packet loss network connections. So when your devices are using IoT Core with MQTT, you can connect globally to our endpoints. And you have also global data access with Cloud PubSub. And I will show you more information on this in an architecture slide later and real end-to-end architecture. The second part of Cloud IoT Core is the device manager. So you may have one device or 10 devices, but you may have 10 million devices. You need to know where they are. So you have a device registry where you create and register those devices. You can have their configuration details there. You manage the keys and certificates with the devices. You can update their configuration. And of course, security-wise, you need to have role-based access control. So who or what system or what software or what hardware can communicate between your systems. And of course, the Cloud IoT Core gives you a nice console to use it, as well as APIs for programmatic access for all these functionalities. At the end of the day, it's pretty much all about this. You have small IoT devices, typically they are small and cheap, and they produce data and they handle data. So you will have an onslaught, a wave of data coming from these potentially thousands or millions of devices. And that's really one reason why customers like Google Cloud Platform, because we have really nice services to help you manage that data. So here in this animated slide, you can see a quite typical architecture of an IoT solution where it's not just about the devices on the left. It's even more about the data that those devices are producing and what you can do with the data then. So on the left-hand side, you can see a device. Let's say it's a robotic arm or something in a manufacturing plant. Maybe it's streaming telemetry, all kind of sensor readings of its health and what it's doing up to Google Cloud. And the first thing that happens is the secure connection from the device, the IoT device, to Google Cloud IoT Core. Maybe they use MQTT protocol over TLS, and it's basically posting sensor readings maybe every few seconds. Cloud IoT Core is then authenticating that the device is the correct device, who they say they are, using the keys. I will talk about that more in the next slides. And once we receive the data, Cloud IoT Core is then forwarding the data to our Cloud PubSub service. Cloud PubSub is a message queue. It's a publish subscribe message queue that is really handy for ingesting data at any scale. It's a global service. It keeps your data packets there for 7 days to give you time to process them. You can subscribe to topics, and then you can start handling your data. And PubSub guarantees at least once delivery of all the packets. And once you have your data stream in real time coming to PubSub, you can then start acting on the data. And in this slide, we have a couple of examples. On the top there, you have Cloud Functions. So Cloud Functions gives you serverless computing. So with very small little pieces of code, typically 1 or 2 pages of code, you can subscribe to these packets in PubSub, all the data coming from your IoT devices, and you can programmatically investigate and look at the data. So Cloud Functions is one way to do that, and it's really nice because it's serverless and easy to use. When you investigate the packets, you can maybe make decisions that based on the data in the packets, I need to do something. That something might be an action that you want to act on the device. So you make a decision programmatically with Cloud Functions and you send a command to the devices. Do something else. Maybe change the temperature, whatever. The other common way then is with data flow. Especially when we have very, very, very large streams of data coming in, you need to have real-time data processing. And data flow is our runner. It's our managed service to run Apache Beam pipelines. Apache Beam is an open source way of developing pipelines for both streaming and batch data in a single pipeline. Now, why would you need this? You need to do things like maybe clean up your data, validate your data. With streaming data, you need to do things like windowing, maybe aggregation, pre-calculating some early results, etc. So you need to start processing the stream of data coming in. Typically, in a legacy manner, you would do ETL with files. You still need to do the same tasks for your real-time data stream, like cleaning up the data. So data flow is a great way to do this. And once you have pre-processed your data, you can then land the data somewhere in a storage data store for further processing. We have many services for that. It depends more on your use case. But here we have a couple of examples. For example, we have Cloud Bigtable. Bigtable is an extremely high performance and large scale key value store. So you can start storing, basically streaming your pre-processed IoT data in Bigtable. And that's really handy for things like time series analytics. And then another option is BigQuery. BigQuery is a large and fast and easy to use data warehouse service. So basically, just like with Bigtable, you can start streaming data directly into BigQuery, directly into your data warehouse. And then that data is immediately available in real time for further analytics using simple SQL queries. So on the extreme right-hand side of the slide, you can then see that we have services like Cloud Data Studio to create nice dashboards and visualizations. Maybe Cloud Data Lab, which are our hosted Jupyter notebooks. Then you can start programmatically with simple Python code, start investigating and exploring your data, creating visualizations. Or you can connect any kind of data visualization tools like Tableau from our partner ecosystem into BigQuery and start analyzing and getting insights. And last but not least is the one on the bottom, machine learning. With Google Cloud Platform, it's really easy for you to create and train machine learning models and then attach those machine learning models to the real-time data stream coming from IoT. Then you can get even more insights and even better functionality to act on the data coming. So you can do things like inference and prediction and classification for the data coming in with machine learning. Now, this is just an example here, but in this session, I'm going to show you a real end-to-end live demonstration. So let's take a look at this end-to-end example, what we have built for you here. Let's start by discussing a little bit the devices. What kind of IoT devices are there in the world? I think there's two kinds of IoT devices. The one on the left is a microcontroller. Nowadays, people start using a lot microcontrollers like ESP8266, ESP32-based chips, maybe Arduinos and similar devices. They are typically very, very small. They're very cheap. They only cost a couple of dollars, maybe a few dollars each. But they start to have things like Wi-Fi, Bluetooth, maybe LoRa, so interesting network connections. But a microcontroller is not a server. It's not a full-blown computer. Microcontrollers don't really have an operating system. They just execute simple code. But there's great benefits for that. They are in a way easier to manage because there's no operating system to manage. You just put your compiled code there and it will be executed forever in a loop. So they're great for example, having cheap sensors all over the place, sensing things and sending you the data using their network connectivity. Microcontrollers are also great for connecting analog devices. Many of the sensors and motors and actuators are actually analog devices that digital computers cannot really handle. Microcontrollers are great for that. And at scale, microcontrollers are great because they are cheap and they are small. So the price per unit is much smaller. The other type or the other kind of IoT devices are the microprocessors on the right. Boards like BeagleBone, Raspberry Pi, etc. They are actually full-blown computers. So they have typically multi-core CPUs. They are running a full, typically Linux operating system. They are servers. They are just very, very small servers. They are cheap. They are like $30, $40, $50 maybe. But they are maybe 10 times more expensive than the microcontrollers. So usually the microprocessors like a Raspberry Pi are used in a different kind of scenario than microcontrollers. Microcontrollers might be your sensor network, and microprocessors like Raspberry Pi or BeagleBone do something heavier. Maybe they also already do some analytics and actions locally on the device, maybe in drones or robotics or augmented reality scenarios. So they are for heavier activities. How do you actually connect your IoT devices to the cloud? It doesn't really matter how you do that as long as your device has an internet connection. Then we can ride on top of that internet connection from the client up to Google Cloud. In practice, there's many wired and wireless protocols and connectivity methods based on the different devices that you choose. You can see here things like LTE, 3G, ZigBee, Bluetooth, Wi-Fi, LoRa, even RFID, Eddystone, etc. on the wireless side. On the wired side, you can use serial connections, Ethernet, etc. It really depends on your use case. And because the devices are typically small, and the network connections you have are restricted bandwidth and maybe more expensive, using the full-blown internet TCP/IP, HTTP, HTTPS stack would be very heavy on those devices. And many of the microcontrollers cannot really handle the full internet stack. That's why it's really popular in the world of IoT to use MQTT as the transport protocol. It's significantly smaller, less chatty, more compressed than the full-blown internet protocol stack. So it's great for these little devices. It also saves a lot of your battery power and processing energy. So it's just faster and lighter. So this is the preferred protocol with Google IoT Core from your small devices up to the cloud. Then how do you actually connect those devices? Well, it depends whether your devices have their own individual internet connection or not. So in this slide here, we have the scenario of scale-out IoT architecture. Here you have many devices somewhere in the field, and each one of them has its own internet connection. Then you can scale out the connectivity and also scale out the data coming from the devices up to the cloud. Each one of them is talking directly and individually to Google Cloud, to our IoT Core platform. The protocol is typically MQTT, secured with TLS, transport layer security, using certificates and keys. If, however, your little microcontrollers don't have their own internet connection, or it would be too expensive to have one for each one of them, maybe you have like a campus area network where you have some kind of connectivity from your microcontrollers to a central building or central location. And this central location near the devices has then a gateway or bridge up to the cloud. Maybe a Raspberry Pi, maybe a full-blown server, for example. So then these little tiny microcontrollers will be sending somehow, maybe with a serial cable, local radio connection, their sensor readings to this gateway node. And this gateway node is then connected to Google Cloud using its internet connection. That's the other popular connectivity method that customers usually have. Okay, no more slides. Let's move to the live demo. So what do we have in store for you in the demo? Well, I wanted to be green. I wanted to build an example solution that is green and something typical in IoT. So I chose to build for you a solar farm, a solar panel farm. So first we need the solar panels. We need solar generators. And I have here on the table a couple of prototypes for you. The first prototype is like this. The microprocessor in question is a Raspberry Pi. And there's a new model now called the Zero. It's much smaller than the normal Raspberry Pi. And it's not just the Raspberry Pi Zero, it's called the Zero W. W means wireless, so it has a Wi-Fi and Bluetooth connectivity built in. So it's a small Raspberry Pi with Wi-Fi and Bluetooth. On top of that, we have an expansion board. It's called a hat or P-hat. And in this case, in the first device, it's a Pimoroni Environment P-hat. So it's a little attachment board that plugs directly onto the Raspberry Pi Zero W, and it adds some sensors to this picture here. So this hat here has sensors like light level, that's our solar panel, temperature reading, air pressure, accelerometer, and compass. So basically we can know the orientation and tilt angle of the solar panel, as well as ambient temperature, air pressure, and of course the solar panel, which in this case is the light sensor, letting us know how bright it is in this environment here. And on the Raspberry Pi Zero W, it's running Linux, it's running Debian or Raspbian. And on that, I've installed the Google Cloud IoT client libraries. In this case, I'm using Python. That's my personal preferred language here. The second prototype is very similar. It also has a Raspberry Pi Zero W, just like the first one, but it has a different hat on top. This one is a Dexter Grove Pi. Grove is a modular system from Seed Studio that we like to use a lot. Basically, it lets you plug and play, basically connect sensors and actuators with easy connectors to your microcontrollers or processors. So in this case, we have the Grove Pi expansion board connected to the Raspberry Pi Zero W. And using the Grove connectors, I'm able to plug in either analog or digital sensors and actuators to my Raspberry Pi. So in this case, these weird dangly things here are the sensors. So we have a six-axis accelerometer sensor here. We have a combined temperature and humidity sensor here, a DHT11, I think. And we also have a light level sensor here. So just like in the first device, we have everything built into this one hat here. In this Grove example, we have external sensors connected to the Raspberry Pi, but providing the same capabilities, the same sensors. And likewise, actually identically, on this second Raspberry Pi, I'm running the same Python software with Google Cloud client libraries. But I only have two devices here. With two devices, it's kind of difficult to demonstrate any kind of scale. So I wanted to also create simulators so that I can test my end-to-end system with better scale. So we need to simulate these solar panels. So for that, I'm using Kubernetes, containers basically. So the same code that I'm running on these Raspberry Pis here, I modified that a little bit, and I run the simulators of the same code in Kubernetes in our Google Kubernetes engine. So then I can spin up any number of containers that are running the same code as the Raspberry Pis, but simulating, generating these sensor readings at scale. And then all of them are pumping their data up to IoT Core and my end-to-end pipeline after that. So with Kubernetes, we can get some scale here. And this is the actual end-to-end architecture that I will be showing to you now. On the left side, we have the devices, these two Raspberry Pi Zeros with the sensors. They are using currently local Wi-Fi and then internet, connecting to Google Cloud IoT Core securely, and posting every second their sensor readings, light level, temperature, humidity, etc. IoT Core is authenticating and then passing through the messages to Cloud PubSub message queue. And then consuming those messages from PubSub, I have Cloud Data Flow, Apache Beam streaming pipeline, accepting the data, consuming the data, processing it, and then storing the filtered, cleaned up data in BigQuery, our data warehouse. And then connected to the data warehouse, I have Cloud Data Studio with dashboards and visualization. And I'm also using Cloud Data Lab with Python notebooks, Jupyter notebooks, to explore the data programmatically with Python. So, without any further ado, let's show you. And just a reminder that instead of the devices, we can also then run containers at scale to generate more sensor readings to the system. So let's now switch to the live demo. And first, I will show you the IoT devices and simulators. So here on the table, we have the two Raspberry Pi Zeros with different sensors. And first, we need to connect to those. So from my laptop here, I have an SSH connection. I've logged in securely to both of these Raspberry Pis, 1 and 2. And all I need to do then is to execute the client side, the IoT device client app that I have running here. That client app is reading the sensors from the device and then posting them as telemetry once a second up to Google Cloud. So let's start this client software on both of these Raspberry Pis. The first thing that happens is that the devices will need to generate a JWT token, JSON Web Token. So the devices have a private key. When you provision the devices, you generate a key pair, public-private key. The Google Cloud IoT Core is then keeping the public key, and you have the private key. When you're connecting your device to IoT Core, you need to sign a token, JWT token, with your private key. And then Google Cloud IoT Core, when it receives the message, it authenticates your device using the public key. So it's asymmetric public-private key encryption, authentication. Once that's done, the devices can then start sending data up to the cloud using MQTT, but not insecure, but MQTT over TLS, Transport Layer Security. So here we can see now both of these clients, both of these Raspberry Pis doing something. You can see here the message payload. So both of them are sending temperature, lux is the light level, timestamp, once a second, client ID, Raspberry Pi 0, W1 and 2, humidity, air pressure, and XYZ, which is the accelerometer orientation of the device. Now one of the devices doesn't have a humidity sensor and the other one doesn't have a pressure sensor, so they are posting 0 for those values. Slightly different sensors between the two devices. So now we can see that we should be getting data up into the cloud. Where does it go? Let's now move to Google Cloud IoT Core. First, if you haven't seen it, this is the Google Cloud Platform's console. So this is the landing page, the dashboard, if you will. From here, you can see an overall status of your project here. And on the left side, you can jump to these individual services that we have in the cloud platform. The first one we are interested in is IoT Core. So my devices are now connected and they should be posting data once a second. Where does it end up? In my IoT Core project. And in IoT Core, you have the concept of a device registry. The registry is a collection of all the devices doing a similar thing for the similar use case. So in this case, I have created a registry called Solar Farm. It's very easy. Run through a simple web wizard here or use APIs to create your device registry. And the registry is a collection of devices then, all doing the same thing. In this case, they are solar panels or solar generators. What do we have here? Well, first of all, in this registry, you can see that you can choose which cloud region to run it in. What are the protocols that you want to support for your registry? In my case, I'm using only MQTT. Then you can see that when your devices are sending data up to the cloud, where does it go? If everything is okay with authentication, the data is then passed from IoT Core to Cloud PubSub. And this is the particular topic in Cloud PubSub, Solar Farm. That's where you send your data from the devices. That's why it's called the telemetry PubSub topic. The second PubSub topic is then an optional one for you to manage your device's state. If you want to change the state of your devices, like on or off, or change the temperature of an air conditioning unit or something, change the color of a traffic light, whatever, you can use the state topic then to communicate back to your devices what they should do. Of course, you can monitor all the logs and events in Stackdriver. And then for all your registries, you then have your devices. So these are the physical devices that I have registered in this registry. Actually, the first ones are physical Raspberry Pis, but the last one is the Kubernetes simulator. That's also a device here. You can see that each one of these devices is allowed to communicate. And if I select one of them, we can see some statistics of this particular device. This is the first Raspberry Pi on the table here. We can see that it is sending heartbeats and it is sending telemetry events. So the latest timestamp for these actions is right now. And you can see that the device already has a key pair, public-private key. This is used for the JSON Web Token generation and authentication of the device. That's about it. So it's quite simple. Once your data is coming in to IoT Core is then passing it to Cloud PubSub. So here we can see that in this case, I have the Solar Farm topic. This is where the data is coming in. How do we then process the data? In my case, I'm using Dataflow, real-time pipeline handling the data in PubSub. Cloud Dataflow is this managed service that is running Apache Beam, and it's automatically subscribed to this topic. So when I started the Dataflow pipeline, Dataflow service connected to this PubSub topic. We can see the connection here. We can see the subscription. So I didn't create this subscription. When I started the Dataflow pipeline, it connected to this PubSub topic. Of course, in Dataflow, I had to define where to connect, which PubSub topic to connect to. So let's take a look at data flow then. So after the messages go to PubSub, I'm doing the filtering, the aggregation, the windowing of the data in real time using Apache Beam. And I'm running it in Cloud Data Flow here. Cloud Data Flow is what Google uses internally as well for real-time data processing. So basically with Cloud Data Flow, you create a graph. That sounds a bit fancy, but basically you create the pipeline that defines what you want to do with your data coming in. It's officially called a DAG, Directed Acyclic Graph. That sounds very fancy and confusing. In practice, it means that you define a flow for your data, your actions. Acyclic means that it's not allowed to loop back. Because if you have an action, and then you go back, go to one, you might have an eternal infinite loop and a deadlock. So your graph cannot have a loop like that. Anyway, you basically just define all the actions you want to do for your data. And the first action is quite logical. We want to read all the data packets from PubSub. So as we are posting data from these devices, goes to IoT Core, goes to PubSub, and then this first action that I have highlighted here in data flow is picking up those packets from PubSub and starts processing them. The first transformation or first action is very simple. Just read the data from PubSub. And then you can see that I'm branching. With data flow, you can also branch handling the data. So you can have multiple use cases for the same data. You can have real-time visualization dashboards. You can have aggregations. You can store data in data warehouse. You can attach machine learning models, all to the same real-time data stream by branching in data flow. The first branch here is what my data flow expert colleague Reza always recommends me to do. Store everything in BigQuery first, just in case. So the first one here is simply reading all the data from PubSub and just writing it into BigQuery as a table row, just in case, without any further processing. So then you have all the data stored. The second branch is then doing real-time analytics. It's applying a time window, 60-second window, so 1 minute window. Because you have a real-time data stream, if you want to calculate aggregates like averages, minimums, and maximums, average when? So typically you apply a window then. So I have applied here a 1 minute window. And then I group by key. So for example, I can use the devices or sensor readings like temperature as a key. And then I calculate a minimum, average, and maximum for all the sensor readings in that time window. And then I write those aggregated results in another table in BigQuery. So then I have two tables, one with all the raw data, just in case, and a second table with every minute, minimum, average, and maximum values. That's maybe easier for a lot of the analytics and visualization going on then. So that's data flow. And if we look at the data flow pipeline running now, we can see that currently we have one worker and auto scaling has been activated. So currently my data volume is quite small, so the system has scaled down the number of workers to 1. Maybe 2 is better for production systems to have just in case redundancy and avoid single points of failure. But then if you need more processing horsepower in your pipeline, data flow can auto scale and add more workers to make sure that you're not falling behind real time. Are we actually handling any packets? Well, if we look at the first transform read from PubSub and we zoom into the messages handled, every few seconds we are updating the counters here. You can see that we have handled 41 million messages so far in this pipeline. And the last number here, the end of the number shows you that every few seconds the counters are increasing. So we are getting a little bit of packets from these 2 Raspberry Pis now, both of them sending once per second. So that's data flow in a nutshell. Where does the data actually land? Data flow is processing the data and storing it in BigQuery, our data warehouse service. Basically streaming into those tables in BigQuery. In BigQuery you have a data set, which is a collection of tables. Then it's very simple. You just create tables with a certain schema that you want. This particular table is the raw storage of all the data coming in. It's called the solar farm table. You can see the schema. So we have a timestamp for all these solar panel readings, client ID, so which solar panel is it, and then the sensor values, temperature, light level, etc. If you look at the details of this table has 53 million rows here. And actually some of the rows are still in the streaming buffer, so it's more than 53 million rows. We can look at the preview of the data directly in the BigQuery interface here. And you can see that yes, we have a timestamp, we have a client ID, pi0 grove, and then some sensor readings, etc. We also have the averages table. So the second branch of data flow is doing windowing, aggregation, group by key, and averaging. Those results are written to this table then. So let's take a look at the preview of this table. This looks a bit different. So here we have every minute readings. And let's actually execute some SQL queries to show you how it can look like. Here in Google BigQuery console, I can access my previous queries. I can store some queries. So let's open this example query that I made earlier, where we select all the data from this solar farm table for these two particular devices. And we order by timestamp descending. So we want to see the 100 latest entries from these two physical devices. Let's execute the query, run the query in BigQuery using the console. And then you can see the results here. So 0W2 and 0W1 are these devices. And here we have the latest temperature, light level, and other readings. So this way you can verify that you have the right kind of data in BigQuery. Once you're confident that your data is in your data warehouse, you can then attach visualization and analytics and insights tools to BigQuery. Let's take a look at one of them now, Cloud Data Studio. So from BigQuery, we have a concept of a data warehouse. Then with simple SQL queries, you can connect things like Cloud Data Studio to your tables. So Cloud Data Studio lets you create dashboards like the one here with easy and simple visualizations. And all the data in this dashboard, all these graphs, are a direct result of queries against BigQuery. So let's take a look. What kind of dashboards and visualizations can we create with Data Studio? So here we have one that is showing the average hourly temperature and humidity readings, total sensor readings, 55 million, because some of them are in the streaming buffer. Some correlations. Is there any correlation between light level and ambient temperature? Maybe not. I'm not a data scientist, but it doesn't look like there is any correlation. This is a nice graph showing the average light level, average brightness by hour of day. So it really varies according to, of course, how the sun is going up and down. Any temperature and humidity correlation? Maybe not, again. And then some fluctuations. So you can also make dashboards that show you if you have any issues with any of your devices, not just the actual data you're interested in, but also to uncover any problems with your fleets of devices. And then you can, well, go and fix them if they are broken, for example. So creating these nice visualizations and graphs is easy with Cloud Data Studio. So that's nice. In addition to that, what is getting really popular these days is that people are using Jupyter notebooks. Basically doing a bit of coding and a bit of visualization in a nice web interface, like an interactive web page. And we have a managed service for that called Cloud Data Lab. So with Cloud Data Lab, you can, within your project, with your team, collaborate on your data. So basically connect your Python code directly to your data, for example, in BigQuery, and then start exploring your data, visualizing it, and collaborating with your colleagues on that. It started in the scientific community, and it's getting really popular now, even with enterprise businesses and startups. So here we are in Google Cloud Data Lab, our managed and hosted Jupyter notebooks. I have created an example notebook that we can briefly see here. So basically it's Python code in an interactive web page. You can just add, for example, a text box here. Hello webinar folks. and that's it. And then in addition to text, you can also add some code. So here we have the first code cell, and you can see that basically we are using the BigQuery client here directly in this notebook, and we execute a query. And you have the SQL query here. So we select the timestamp, minimum, average, and maximum of looks, the light level, from the averages table, group by timestamp and order by timestamp. And if I play or execute or run this cell, the results of that query, so it's a live query to BigQuery, we get back a response from BigQuery service, and then we can act on the response data. In this case, the action I'm doing is a chart. So I'm creating a simple chart to visualize those results. So let's create a chart and look at the recent minimum, average, and maximum light levels. There we go. Let's see something else. Minimum, average, and maximum temperatures per client. Execute query, execute a chart on the results again. There we can see that we have some differences in our simulators. Some of them are slightly warmer and some of them are slightly cooler temperature. They are simulated readings. This one is showing quite a powerful one. The next one, the histogram. So basically the query to BigQuery is very simple here. It's a simple select of one column, temperature. So we just say to BigQuery, give us all the temperature readings, last 1000. And then we actually do the computation and analytics here in the notebook by creating a histogram chart. So we can see the distribution of different temperature levels for our solar panel sensors. And maybe last could be a fun one. Let's have a nice chart which is a gauge showing the latest readings from these two physical Raspberry Pis here. This looks very nice. So we have 27.6 degrees centigrade here in this room. It's about 2,200 lux light level from these lamps, and the air pressure is 1,011 millibars. There we go. So that's Cloud Data Lab. It's really popular. Also, I mentioned to you that you can collaborate with your colleagues. So as part of Cloud Data Lab, it also has built-in Git version control functionality. So with a simple button click there, you are brought to this ungit interface. So it's built into the managed service. You can commit your changes to the notebook, and your colleagues can then easily check out within the same project a copy of that, collaborate and commit changes back. So you can collaborate in a nice way using standard Git, your Data Lab notebooks. Now I'd like to show you one more thing. We are running the data now from these two real Raspberry Pis. How about Kubernetes? So in my terminal here now, let's ask with the gcloud CLI, do I have a container cluster, Kubernetes engine cluster? Yes, I do. So I have one cluster with 5 nodes, ready to run containers. But however, if I ask from Kubernetes, are you running any pods? Are you running any containers? The answer is no. Kube control get deployment. Currently, I'm not running any deployment in Kubernetes. So let's create one. I ask Kubernetes to deploy my solar simulator deployment. So I have a definition YAML file here. I'll briefly show you. Very simple. It's just pointing to a container image that I made. That container image has the simulators for these solar panels. So now, if we ask from Kubernetes, do you have a deployment? Yes, we do. There is a solar simulator deployment and one container is running. Let's scale the number of replicas to, for example, 10. Let's ask for 10 containers or 10 pods running the same simulator. And now if we check the deployments, we have 9 already available and the last one is starting. So there we go. It's really fast and really easy to use things like Kubernetes and containers to create simulators and then verify and test at scale that your end-to-end system can actually handle the data, and always test at least to the expectation of customer traffic or even double that or 10 times your expectation. Because if you have success, you don't want to have success failure. So please do performance tests, unit tests, etc. Due diligence before you go into production. So now the number of messages per second is significantly higher going to our end-to-end pipeline, because now we have containers generating a lot of traffic. So we should see here that the number of messages per second is significantly increasing here. But because all the systems that we are using here are automatically scalable and serverless, it's very easy using Google Cloud to manage your data pipelines end-to-end without any hassle from your side at any scale. So with that, let's go back to the slides, and that finishes the demos. I hope that you enjoyed the end-to-end demo. And with that, thank you, and we can move to the Q&A now. Jay, if you'll join me here, please.
Thank you so much, Markku. That was super cool. And as I said, earlier, whenever Smart Parking was talking about IoT, they asked for some demos. I think you gave it to them in spades, because not only did you show IoT Core, you talked about sort of like the entire serverless end-to-end. And one question that we had, which might seem simple on the surface, but actually I don't think is as simple, which is, what is serverless? Like, what do you describe as serverless?
It's a good question. At the end of the day, of course, it is still servers. So Google have massive data centers with huge number of servers running everything. So servers are there. But serverless is from the customer and user point of view, that you don't need to manage servers anymore. Now, in my old life, in my previous life, I used to be crawling under data center floors, pulling cables and literally assembling servers from their components. That's a lot of undifferentiated heavy lifting. It used to take me 1 or 2 weeks just to get the servers running the applications we wanted. With serverless services, like the ones I showed you today, you can focus on your code. You can focus on your features. And this undifferentiated heavy lifting of all the underlying stacks can be automated. And the automation is also helping you in operations. It likely makes your system more reliable when the system is detecting the changes and automatically acting on those system changes.
Right. And it also helps from a pricing perspective as well, because once you have those serverless architectures in place, then you don't need to worry about those servers, and you don't have to pay for the underutilization of those servers as well.
Exactly. Plus agility. So, like I mentioned, in the old days, I used to spend days and literally weeks building the systems. Now, you can deploy your systems in seconds, and you can really focus on iterating on your features and fixing your bugs.
Right, and scaling as well, right? So 1 query per second, 1 million queries per second. Yeah. When you're using a good serverless architecture, those things can scale automatically for you.
The same pipeline that I showed you just now, our YouTube viewers, I tested at 100,000 messages per second, simply by increasing the number of containers, generating more load. And I didn't touch anything else. Everything auto-scaled.
Okay, fantastic. So another one was, someone just asking about use cases in general, and maybe I'll sort of pivot that question. Like, what are some of your favorite IoT use cases?
Yeah. My favorite are the ones where people are really inventing some amazing use cases that nobody thought of. Like here in Singapore, we have a lot of rental bikes that you can just take a bike and hop on, and basically the bike has a microcontroller and a mechanical lock that the microcontroller controls. And you can book the bike using your mobile phone, scan a QR code, and your phone's internet connection is then used to communicate to the cloud to open the bike. And your phone's Bluetooth connection is used to command the microcontroller to open the lock. So this is a really, really handy way, and they went immediately into scale. And these kind of use cases are amazing. And a lot of the IoT real use cases are related to industrial IoT. So manufacturing, field sensors, air quality sensors. And in all these use cases, there's always a lot of scale. There may be thousands or millions of sensors.
Right. And actually, even in our own data centers, right, we're actually using a lot of those technologies to improve the efficiency as well.
By adding machine learning, slapping machine learning on top of that data to improve the efficiency of the data centers.
That's right. So yeah, so if you walk into a Google data center, I know most people think about data centers, they think about these refrigerators, but if you walk into a data center floor at Google, they're actually quite warm, right? Because we're actually sort of balancing the efficiency of the data center along with those failure rates in order to make sure we have those, have that data center efficiency.
Everything is data-driven. It's interesting, Google data center folks even analyzed what is the optimal temperature for the lifetime of hard drives.
Yeah,
and it's much warmer than we expected, maybe.
Yeah, absolutely. Great, thanks. So you talked about MQTT. You talked about some of the benefits of that, but there are also a lot of people using HTTP as well. Yeah. So can you tell us sort of about what the trade-offs there are there?
Probably for HTTP, the use cases a web developer who's very familiar with HTTP. They just want to continue using the language they're familiar with and the protocol they're familiar with. Then IoT Core supports that easily. You can use HTTP end-to-end. But in case you have a really constrained microcontroller, this is not even a microcontroller. These are still microprocessors, but microcontrollers are really tiny chips. HTTP stack is too heavy for those. Then you don't have an option. You need something more compact, more optimal, and MQTT is the best for that. But don't worry, MQTT is very easy to learn because it's a very simple protocol, and we have good client libraries and examples how to use MQTT.
Okay, fantastic, thanks. And there were a lot of questions around, speaking of sort of like these more sensor-based devices, these sort of unintelligent devices, security. How do you manage those on those devices? And the second part of that question was, and then how does the device configuration in Google Cloud IoT Core help you manage those types of devices?
Yeah, good question. So I need to try to take this in phases. So let's look at the device itself first. Well, try to have physical security on the device if you can, but it might be in a field of rice crop somewhere, so that might be difficult. So then you need to make sure that if somebody tampers with the device or takes the device with them, tries to read the memory or storage, you still need to have good security. So first of all, when you provision devices with IoT Core, you provision the device in the cloud, but you also generate a key pair, public-private key. That private key is used on the device to sign the token, JWT token, when it logs in. You need to secure that key. So many of the boards actually have a crypto chip, trusted platform module chip. So you can store securely the key on the device using the TPM chip. That's one option, if the device has to be literally out there with poor physical security. Then when the device is connecting to Google Cloud, it uses the private key to sign a JWT token, JSON Web Token, and authenticates with Google Cloud IoT Core. Then Cloud IoT Core knows that this is the proper device because only that private key was able to sign it so that we can open it with the public key. Once the authentication is done, the device is allowed to communicate. But it's again secure end-to-end because somebody might be trying to do a man in the middle. So then we have MQTT over TLS, transport layer security, so that it's end-to-end encrypted. And once you then have these devices connected, you want to manage the configuration of them.
Right.
So IoT Core also lets you manage device configurations. You update the configuration programmatically from your apps, your backend systems. IoT Core is transmitting this new configuration to the device. Your client code running on the device has to then accept. We have a simple one line of code client library to accept the configuration. But the configuration can be anything. It's just a blob that you transport. It can be JSON, it can be whatever. It's up to you what is the payload, what is the configuration. Typically, it's something like a JSON structure with some new changed attributes. You programmatically handle that on your device side and basically act on it. But that's up to you. What IoT Core does is it lets you manage these configurations and transport them to your device.
Okay, speaking of that, so how do I do that? How do I actually send commands then to that IoT device?
Well, the devices are connected to IoT Core, but not just one way. It's a bidirectional communication channel. So with MQTT, for example, you have a topic where you're posting messages to the cloud, but you also subscribe to listening to messages on other topics like the state changes and the configurations. So basically using the same MQTT, your cloud apps or IoT Core can then send a message to the MQTT topic and your device is listening on it. So it will simply receive an event and then you have an event handler in your code and you simply read the message and you process it.
Right.
Bidirectional.
Right. So another advantage of MQTT is you have that publish subscribe model built into the protocol.
Yes, and it's very simple, very easy, because it has to work on really tiny devices like Arduinos. So the number of lines of code is very limited and minimal, which is good for your agility to develop some features.
Okay. And then the last question, the difference between MQTT quality of 0 and 1.
Yeah. So good question. So in MQTT, there's different quality of service levels. Basically, that's a bit like UDP and TCP. So MQTT quality of service 0 means fire and forget. It's a bit like UDP. So we send a message, but if something happens to the message in transport, it's lost. It's not retransmitted. Now, if a device is, for example, sending sensor readings every second, you don't probably really care about resending lost packets. Anyway, it's kind of delayed then. So in that case, maybe 0 is enough. But if, for example, you want to send a configuration change to your device, you want to make sure that the device can receive it. So then you would use quality of service 1, which means guaranteed delivery, at least once delivery. So then if something is lost, we know that and it's retransmitted.
Okay, great. Thank you very much, Markku. Is there anything else you want to add?
Start hacking.
Start hacking.
Start using these things. Buy some microprocessor, buy some microcontroller, buy a Raspberry Pi, and follow our examples in cloud.google.com IoT, and just run through these getting started things and connect the device to the cloud, and it's really good fun, and we hope that you enjoy it.
Great. So please fill out the feedback form on your right, my left, to give us some feedback on what you thought of this session. Please ask lots of questions below. We still have some time to answer a couple of questions. In about 4 minutes, I'm going to be rerunning my session from this morning where I give you an overview of Google Cloud Platform. And later on today, we have a fireside chat with Omise talking about how they moved to start using Kubernetes and getting 5 nines of uptime on their services. And we'll also be talking to Gojek to talk about data warehousing. So we're going to delve a little bit further into BigQuery, which was mentioned briefly by Markku in the IoT demo. And we'll talk about how you can actually use that as a data warehouse and how you can actually get some insight out of all that data that you're collecting. So thank you very much. Please, if you found these things useful, please forward the links to your friends, get them to register and join us for the sessions this afternoon. Thank you very much, and I'll see you in a couple of minutes.
Thank you.